This is the integral that many of you guys have been waiting for, the integral from 0 to 1, ln x times ln of 1 minus x dx. And if you haven't done so already, please pause the video and try this first. Okay, how did you guys do it? Maybe with some integration by parts, maybe with some substitution, and maybe you also notice that the input here is x, and the input here is 1 minus x, and this integral goes from 0 to 1. So maybe you also try to do this with like some kind of symmetry, right? Because at the end of all the work, we should just have a number for the final answer. And I know this integral must be well decided, otherwise, you know, it's not a legitimate integral in the first place. So we must have a good answer for this, all right? But anyway, I wanted to share my solution with you guys. And of course, you can leave a comment in the comment section and let us know like how you approach this. I noticed that I have the ln of 1 minus x. And seriously, I don't really think that I can integrate ln x times ln of 1 minus x in the sense of finding an antiderivative for that, right? But I do notice that I can find a power series for this guy, right? And remember, a power series is in the form of the sum and then some constant and then times x to the nth power. And when we have x to the nth power times ln x, in fact, we can integrate that by integration by parts. So that looks pretty legitimate. And also, this integral is only going from 0 to 1. So the power series for this guy is also going to converge, right? And some people may be wondering, is this a convergent integral in the first place? And let me just tell you guys, it will converge, all right? I will leave the detail for you guys to figure that out later on. But here we go. Let's go ahead and find the power series for this guy. And of course, I have to use my best friend, namely 1 over 1 minus x. And this is going to tell me this is the sum when n goes from 0 to infinity, and that's x to the nth power. And from here, we can just go ahead and integrate both sides with respect to x. And this is how we can get the ln, right? On the left-hand side, when we integrate this, we get ln. And I'm going to just open a parentheses and put this inside because we just care about x going from 0 to 1, right? So the input here will be positive. I don't need the absolute value. And remember, when we integrate this, the derivative of 1 minus x is negative 1. Be sure to divide by that derivative. So I will just attach a negative 1 in front, like this. And also, we are integrating both sides. So technically, I should put down a plus c on one of the sides. I will just put it on the left-hand side. Anyway, on the right-hand side then, we are integrating this guy, right? So the truth is that you can just integrate this term by term, and that's one of the theorems. And to do so, you can just add 1 to the power and divide it by the new power. So all in all, we still just have the sum when n goes from 0 to infinity. And this is x to the n plus 1 power over n plus 1. And the plus c, it's right here already, okay? Technically, it's plus c1 plus c2. And you merge them into just one of the c's on one side. And to figure out what this c is, what I can do is, I can just say, let's go ahead and let x is equal to 0, okay? Because if you let x equal to 0, on the left-hand side, you get negative ln of 1 minus 0 plus c, and then this is equal to the sum, and plugging 0 into here, all the terms will give you 0, okay? Because the first term is x to the first power, so you have all the zeros right here. And this is just 0 plus c is equal to a bunch of 0, so c is equal to 0, okay? So this is the legitimate way to work this out. And now, I don't need to worry about this at all because c is just 0. So I will erase all that. And you see that I have negative ln of 1 minus x. This is just a positive version. So if you would like, you can just multiply by negative 1 on both sides. So I will just do this to save some space. This is equal to negative that. Okay? So now, let's come back to the integral. This right here is equal to the integral from 0 to 1 ln x. And I'm going to plug in this for that. And let me just bring the negative out to the front right here. Okay? And then I will just put this down here for this. So we have the sum when n goes from 0 to infinity, x to the n plus 1 power over n plus 1 for that guy, and then dx. And we know this is legitimate. This is going to work because for our best friend, the radius of convergence for this is 1. And when we integrate, the radius of convergence stays the same. Okay, so you know this is going to be legitimate. Okay, now, in the summation world, this is the inside of the n world. And inside of the integral, that's the x world. What we are going to do is the following, okay? Let me just look at the lnx. I will invite this inside here, okay? I will invite the lnx into the summation world because in here, the n is the only thing that matters, right? That's the variable in the summation world. So I can bring this inside. Lnx is just like a constant almost, right? Not exact, but yeah. Anyway, this is negative. Let me just keep it as the red negative. Why not? And we still have the integral from 0 to 1. And let me write down the summation when n goes from 0 to infinity. And let me put down this first, namely x to the n plus 1 times ln of x, and then all over n plus 1, and then we have the dx right here. Okay? So far, so good. Now, what's next? Well, I do notice that x to n plus 1 power times ln x, that's something that we can actually integrate with integration by parts. And what I want to do is, I would really want to switch the order of the integration and the summation. And in fact, we can do so, and the theorem is called the Fabinian theorem. And so I'm just going to switch that, okay? And let me just write down the detail. Well, not the detail, I mean, let me just write down the work for you guys. First of all, I still have the negative right here. And then I will do the summation right here now. And then n goes from 0 to infinity. And you see, for the integral, n is just like a constant. And I'm going to take that out first of the integration sign. So let me write down the 1 over n plus 1. All in all, I just want to focus on the integral of this times that and dx. So let me put that down right here for you guys. Integral from 0 to 1, x to the n plus 1 times ln x dx, like this. And now we have to put down the correct parentheses. We are going to do this first. But remember, everything is still inside of this summation. So I will put down a parenthesis like that. And once again, all I did was I first take out the 1 over n plus 1 to the front of the integral right here. And remember, after we finish this part, we do the summation. And we switch the order of the integration and the summation because of the Fabinian theorem. So far so good. And now this is something that we have a better hope, right? And I will work that out on the side with a blue pen, of course. Let's do this with integration by parts with the DI method, okay? So for this guy, I will just put this down right here. Let me just go ahead and put down the D and the I. Which function shall we integrate? I'm not going to integrate ln x because that requires integration by parts. I am going to differentiate ln x, and then I will integrate x to the n plus 1 power, okay? And then don't forget the plus, minus, and differentiate this guy, we get 1 over x. Integrating this guy, we add 1, and then divided by the new power, so that's n plus 1 plus 1, which is 2, of course. So that's always fun to do. X to the n plus 2 power over n plus 2, okay? And I'm just going to work out this integral for you guys on the right-hand side right here, okay? The integral from 0 to 1, x to the n plus 1 times ln x and dx is, you do this times this first, so that's ln x times this, which is x to the n plus 2 over n plus 2. And don't forget, the product of each row is still an integral. And this is the minus of that, so it's minus the integral 1 over x times this guy, which is x to the n plus 2 over n plus 2 dx. And remember, this integral is originally going from 0 to 1. So this is the first part of the answer. We have to attach the 0 to 1. We have to plug in these values now. And also, this integral has to still go from 0 to 1. Let's take a look at this part. I'm just going to plug in the 1 into all the x, so this is ln 1 times 1 to the n plus 2 power over n plus 2. This is nice because it's going to be 0 because thanks to ln 1. But anyway, I'll show you guys all the work. And the minus, plug in 0, ln of 0. And this is going to be a trouble already because what is ln 0? It's undefined, right? So right here, technically, what we're saying is 0 plus. Because we're going from 0 to 1, the positive version, right? From 0 to 1. So it's 0 plus. So this right here, we actually have to deal with this with limits. It is approaching to negative infinity. And if you plug in 0 into here, we get 0, technically 0 plus, raised to the n plus 2 power over n plus 2. Okay? And just be patient. Anyway, and then minus this integral from 0 to 1. And I can reduce this, so this is this, and that it becomes n plus 1 altogether, right? So let me just write down n plus 1 for the power right here over n plus 2, and then dx. Okay, so now, this right here, as I told you, it's equal to 0. This is wonderful, I love this so much, all right? So this is 0. Minus, but what's this guy? Unfortunately, we have to provide some additional work for this. We have to use L'Hopital's rule to argue that, to convince everyone that this right here, it goes to a certain number. Because we're taking limits, okay? So here is just on my note on the side. So notice, what we have to do is we have to take the limit as, you can still use x, doesn't really matter because you just need to figure out the value for this. But yeah, why not? Let me just use x. Going to 0 plus though, okay? And then you have to look at this expression, ln of x times x to the n plus 2 power over n plus 2, okay? So we have to work this out real quick. And of course, let's clean this up because this is a negative infinity times 0 situation, okay? So what I'm going to do is, I'm going to bring the n plus 2 to the front, so that doesn't bother us. That's just like a number in the x world. And we will look at the limit as x goes to 0 plus. And let me leave the ln x on the top, okay? And I will bring this down to the denominator. But that will be a negative exponent, okay? So this is going to be x to the negative n plus 2 power like this. Now, this is in the form of negative infinity over infinity, okay? Because the negative power right here helps us to be an infinity. So we can use L'Hopital's rule. So let's go ahead and do the ddx, okay? So this right here, hopefully I still have enough space. This is 1 over n plus 2. And once again, this is by L'Hopital's rule with infinity over infinity. Technically, it's negative in the front, but doesn't really matter. We still take the limit as x goes to 0 plus. The top here is just going to give us 1 over x. And the bottom here is kind of tricky, but it's okay. You bring this to the front, so it's negative n plus 2. And then x to the negative n plus 2 minus 1 power like this, okay? But anyway, what you can do is the following. This is just going to be 0, seriously. But I will still show you guys the work. This is the limit. We'll still have the I still have the 1 over n plus 2. The limit as x goes to 0 plus. And, okay, I will leave this 1 over x. And this is negative, so let me just put a negative right here. Times, I will leave the n plus 2 down below here. Times, this is going to be up to the new exponent, right? So it's x to the positive now, n plus 2, right? And then this will also be up to the positive exponent, so altogether is n plus 3. But seriously, by now you should seriously see this is 1 over n plus 2 squared. You bring this to the front, bring the negative to the front. The limit as x to the x goes to 0 plus. Cancel this with one of this out, so this is x to the n plus 2 power 0, okay? Alright, it's 0, yeah? But anyway, this right here, it's the 0 right here. So just depends on how much work you want to show. I could have said, okay, watch my other video, I'll do this on the video and that's equal to 0, but yeah. Anyway, this final part though it's a minus, and you integrate this guy, right? So you add 1 to the exponent, and you divide it by that exponent, so it's going to be divided by another x plus 2, okay? I will just put this down right here. So this form is going to give us n plus x to the n plus 2 for the exponent over n plus 2, which is n plus 2 squared. So you just integrate this guy, and now you have to go from 0 to 1. And I know I don't have enough space anymore, but you know, seriously, I'll just come back here to do my work. But why do I want to spend my time over there, right? So now here is the deal. This is equal to, here's the equal sign, yeah? Negative summation, n goes from 0 to infinity, and then parentheses, this is 1 over n plus 1. And this part, I think I'll still do this because I need more space, you will see. This right here, I have the negative. Plugging 1 to the power is just 1, right? So it's 1 over n plus 2 squared. And if you subtract, plugging 0, you get 0. So it's like this, okay? Okay, so just work this out. So anyway, the result of this integral is just that, negative. So I'm going to multiply by negative 1 over n plus 2 square, okay? So that's pretty much it for all that. And now, I reduce this to a crazy series question, right? But anyway, that do sound like easy math. A negative times a negative is positive, all right? So that's nice. So all in all now, we are just looking at the summation when n goes from 0 to infinity, and I just have to care about 1 over n plus 1 times 1 over n plus 2 square, right? How should we take up this? You guessed it, we have to do partial fraction right here, right? So now, let's see if we can do this in our head. This is the summation when n goes from 0 to infinity. And remember, this is a linear term in the denominator, so I'm going to have n plus 1 like this. And then I'm going to add it with, this is a linear term to the second power, it's being repeated. We have to build out the power. So I will have to write down n plus 2 to the first power right here. And technically, I should put on the constant a, and this is another constant b. And then the third one is n plus 2 squared, and we have a constant c like that, right? And of course, our goal is to figure out the ABC values. Let's figure out a with the cover-up method. To do so, I'm comparing this with that. I just need to worry about, okay, I have n plus 1 here. I'm just going to come back to the original and cover this up. And you have to ask yourself, how can you make the n plus 1 equal to 0? The answer to that is you let n is equal to negative 1. So once you cover this up, right, you cover this up, 1 times 1 is 1, doesn't matter. You let n is equal to negative 1, plug in here. So you have 1 over negative 1 plus 2 is 1, and the square is just 1, okay? And for the b, just later on. Because I cannot do the cover up for b. You can do the cover up for n plus 2 squared because the original has the same denominator. I can come back to the original and cover this up and let n equals to negative 2. So when you let n equal to negative 2, you can ruin this, right? Plug into here though, okay? 1 on the top over negative 2 plus 1 just altogether negative 1 like that, right? And take a guess, how can we find out what b is? Well, an easy way to do it, you can just do it with a blue pen maybe. You can just say let n equal to 0 and then plugging 0 into all the n's. So you will see plugging 0 into here. You get 1 times 1 over 4, right? So this is 1 over 4 because that's 1 over 2 and then square. Equal to plugging 0 into here, you get 1. And then plus plugging 0 into here, you get b over 2. And then plugging 0 in here, you get negative, because c is negative already. And you know this is 2 squared on the bottom, so it's negative 1 over 4. And if you do more work depends on how you want to do it. This is 1 over 4, and this is equal to plus 3 over 4, right? This minus that, and then plus b over 2. So what in the world is b? Well, b has to be, let's get the common denominator, so it's 2 and 2. And this is, I don't have enough space, but yeah, let me just write this. Anyway, this is 1 over 4 equals to 3 over 4 plus 2b over 4. And b has to be negative 1. Yeah, right, b has to be negative 1. So you can see that right here, hopefully. All right, so now, okay. This is going to be a telescoping series. And just worry about this guy on his own, right? Okay, so this is real impressive. I can fit everything on the board, so I'm kind of excited. Anyway, this is going to be a telescoping series because you have this minus that, okay? And then the denominator are pretty much the same kind. They are just off by 1. So what I'm going to do is I'm just going to do this. We have the sum when n goes from 0 to infinity. And let's do 1 over n plus 1. And then minus 1 over n plus 2, okay? And then I will add this guy. Well, technically, this is a minus, so I have to subtract the sum when n goes from 0 to infinity, okay? And then we have 1 over, oops, no, not infinity over infinity. Not infinity to infinity. 1 over, the negative is in the front already, n plus 2 squared. Like that, okay? So all in all, this is really nice. And how do we do this? You can write down a few terms and then get the nth partial sum and things like that, right? And the deal is that when you plug in n is equal to 0, the first term is 1, okay? And then you just do da 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 da, you do whatever, and then you have to, let's see, this guy is going to be, well, it's 1, it's 1 minus, well, let's just do it. 1 minus 1/2. It's not 1 turn, it's whatever. And then plugging 1 into next, you get plus 1 over 2 minus 1 over 3, right? And then plugging when n is equal to 2, you get plus 1 over 3 minus 1 over 4, and so on, right? Anyway, you see all the middle terms cancel out. And the deal is that you will end up collapsing all this. You just have the first term, which is 1, minus this guy, 1 over n plus 2 for the nth partial sum. And you take the limit, okay? Seriously, you take the limit, please. The limit as n goes to infinity of this part. And deal with this guy. This is the sum when n goes from 0 to infinity, 1 over n plus 2 squared. Okay, this is easy. This is 1, we're done, because this goes to 0. And notice this part, though. We have to minus. And let me just write this down for you guys to impress you guys a little bit. When you plug in 0 into here, you get 1 over 2 squared. And then when you plug in 1, you get plus 1 over 3 squared, and so on, right? This right here, it's famously equal to a really nice number. I dropped my marker, if you guys noticed that. But anyway, we have the 1 still in the front. But this is not the entire thing. Because technically, I will have to have the 1 over 1 squared plus this. But when I put this down, I change the whole value. Be sure I just minus 1 all the way at the end. And this whole portion here is what? Pi squared over 6. So I will bring down the minus here, okay? Bring down the minus. And all this part, I should bring down the minus in blue. And we are done. You can see already. Minus in blue. And then all this part is pi squared over 6, okay? But in the end here, I minus the 1. So don't forget you distribute, okay? Because I did this and that in the parentheses. So it becomes plus 1. Okay, another interesting part. Look, 1 plus 1 is 2. And then minus pi squared over 6. Done. Be sure to subscribe. Thank you.